Hey guys, it's Miss Johnson, and I'm here to bring you some notes for Section 1E. We are going to start talking about describing position today. Section 1E covers position and percentiles and standard deviation and transforming data and a whole bunch of good stuff. So there's quite a few things that we'll get through. We're going to split this section up into two parts. This is your first part. So starting off, we're going to start talking about percentiles. And a percentile is a method for determining what position a certain data value is given in the data set. So the position is what we're focusing on here. The pth percentile, so the 50th percentile or the 30th percentile, the pth percentile of a distribution is the value with p% of the observations less than or equal to that value. So if we take a look at our first example here, we're going to look at Emilio's test score. It says the score marked in bold is Emilio's score of 43. How did Emilio perform on his test relative to other students in the class? So if we want to find Emilio's percentile, we're going to look at how many points are at or less than or equal to his value. So if I look at his value right here on my little dot plot, we've got the dot plot here. I know that there were 25 students total, and I need to count how many were at or below his score. Now you might notice that it would maybe even be easier to count what was above him. So if we know that there's 25 total and there's only 4 above him, because there's 2 here and that one at like 40, whatever that is, 44, and then the couple at 45 and the one at 47 or 48, whatever that is. So there's 4 above, which means there are 21 below or equal to. So Emilio's percentile can be marked as his percentile is 21 out of 25, or in other words, 0.84, which means Emilio, if I can spell his name right, Emilio, is at the 84th percentile. So here's some tips when you are discussing percentiles and finding percentiles. Percentiles are specific locations. So we want to say that he is at the 84th percentile, not in the 84th percentile, because he's at a specific point in the data. Percentiles are also reported as whole numbers. You're going to round. You're not going to call something the 66.7th percentile. You also want to round down, typically, because it's hard to say that they're at the 67th percentile if they didn't quite get all the way there. So usually you're going to round down to the 66th percentile or whatever your number is. It's hard there because you're kind of ignoring those rules of rounding that that have been burned in our brain for a really long time. And then a high percentile is not always a good thing. Someone who has a cholesterol level at the 99th percentile might need treatment for high cholesterol. So just because they have a high percentile doesn't mean that you are finding a good thing. You have to really pay attention to what your data is actually measuring there. So let's take one more example here. We've looked at this data for lead in the water before. And it says here, once again, we've got the dot plot of 71 water samples taken in Flint, Michigan. And we have, so it says dwellings after the city switched its water supply from Lake Huron to the Flint River. So we're going to calculate the percentile for the water sample with lead level of 9 parts per billion. So 9 parts per billion, I want to look at my 9. It's kind of hard to see here, but it's right there. Hopefully in your notability, you can blow yours up a little bit. But there's my 9. And again, sometimes it's easier to count what's above rather than count up to the 71. I've got a bulk of my data below that 9. So I'm going to count how many are above. So at 10 is 2. That'd be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 are above. And if I take 71 minus 12, that gives me 59. So I've got 59 at or below. So 59 out of 71 gives me my percentile. And when I do that decimal out, I have 0.831. So then the way I would write that out is I would say the water level or this water sample is at the 83rd percentile. Okay. And then a part B here, if we want to go backwards, it says that the US EPA regulations require action to be taken if the 90th percentile of lead level exceeds 15 parts per billion. Based on these data, should we take action? So if I need to know if I take action here, I need to know what is my 90th percentile. So to get your 90th percentile, you're going to take 0.9 times the 71 observations to figure out what position is needed. Again, this is about position. So when I do 0.9 times 71, I get 63.9. And that means I'm going to look at 64, the value of 64, or the 64th position, I should say. So what I need to figure out is, well, what is the 64th position in my dot plot? The 64th position in my dot plot, if I count here, and I can come back and count some of the dots I was looking at before. Let me get rid of this blue that we were looking at and come back here. So this is 71, that's 70, 69, 68, 67, 66, 65, 64, 60, oh, that's 64 right there. Okay, so it looks like the 64th position in my dot plot is equal to 18. Okay, so since it's equal to 18, it's above the 15. 18 is greater than 15. So yes, we should take action. That means there's a problem. Okay, that means our 90th percentile is too high. So action should be taken in Flint, Michigan to correct that. All right, so percentiles are a great way to mark position. Another way to mark position is what's called a z-score. We're going to get into the normal distribution in this part of the unit in the second half of Unit 1. And a z-score is what we use to standardize our data here. Okay, so here's what a standardized score is, or a z-score, in other words. A z-score is another method for determining what position a certain data value is given in a set. Now, z-scores are based on mean and standard deviation. So those are the things that I have to look for when I am finding a z-score. Standard deviation and mean. So the z-score for an individual value tells us how many standard deviations away from the mean a value falls, and in what direction. To find the z-score, this is our equation. We call this data minus mean divided by standard deviation. They call this value. You could also call this data point. Okay, so it's basically what is your x value minus the mean. That's how far away from the mean you are. And then remember that standard deviation is marking your typical distance from the mean. So if I take the distance of a value from the mean and divide it by the typical distance, I get its standardized score, or z-score. So data minus mean over standard deviation, or value minus mean over standard deviation. So we're going to come back to Emilio, and now we're going to look at his z-score rather than his percentile. We already found out that he was in, what was he? He was in the 84th percentile. But what does that mean for his standard deviation? How far away from the mean is he if we put this on a standardized scale? So what I need is, I need the mean, and I also need the standard deviation. So his z-score is going to equal his data value, which is 43, minus the mean of 35.44, divided by the standard deviation of 8.77. If you bust out your calculators, you can do that real simple, quick math. I'm going to get my calculator out. 43 minus 35.44, that's 7.56, divided by the 8.77, and I can divide those two, and I get 0.86. Go away. I wrote the note wrong, number 862. So his z is 0.862. That means Emilio's score is 0.862 standard deviations above the mean. And the reason I say above here is because his z-score was positive. And you can even just tell, like, obviously 43 is bigger than 35. So you went above the mean there. But a direction is going to be really important here. You're going to want to identify, are they above the mean or below the mean? When you get a negative standard deviation, that means that you're below the mean somewhere. So then you're down underneath it. Okay, so that's why it says it gives you a direction as well as how far away from the mean that it is. So let's come back to our lead in the water example, and we are going to now calculate and interpret the z-score for a water sample from Leanne Walter's home, which had a lead level of 104. So she's the one that's way up here, and that looks like a problem, okay? So we're going to use the mean and we're going to use the standard deviation, and we're going to calculate how far she is if she's at 104. So her z-score is 104, because again, it's data minus mean. So 104 minus the 7.31 that was given to us from those summary statistics, divided by the 14.347. Well, 104 minus 7.31, she's real far away. 96.69 divided by the 14.347. 6.74. So our interpretation looks like this. If we were going to interpret this, we would say the water sample from Leanne Walter's home had a lead level 6.74 standard deviations above the mean. Okay, so the water sample, or I could say Leanne's water sample. Leanne's water sample has a lead level 6.74 standard deviations above the mean. Now, you're going to find out when we look at the second half of this unit that that is an extreme outlier. And you can even just see it on the dot plot. Okay, look at all that space between even the next value below, and look at all that space from kind of the bulk of our data. This is a heavily skewed right distribution. We can see, we've talked about this distribution before, and we know that it is skewed to the right. We also know that when you have a skewed distribution, using your mean and your standard deviation can be questionable, and we need the mean and standard deviation to find the z-score. We're going to talk more about that in the second half of this unit, but I want you to recognize, look at how far away she is. And this 6.74 is an extreme outlier. 6 standard deviations, almost 7 standard deviations away from the mean is a lot. That is very unreasonable in terms of a standard deviation. So she's got some real extreme data going on there. And that is, you can see it in the dot plot. We can tell just by the skew. And now we see it with the z-score as well. So let's look at the next part of this example. It says the lead level in a different home's water has a standard deviation of negative 0.37. Find the lead level in that water's home. So now I want to go backwards. So I'm looking at this for a z-score. That's what that is. And remember that z is equal to data minus mean over standard deviation. So if I want to plug that in, that means that my z is going to come over here. So I have negative 0.37 is equal to, I don't know, find the lead level in the home's water sample. So I don't know the data. That's going to stay a variable because I don't know what that is. I know these two things. I have the mean and the standard deviation. So I'm going to say x minus 7.31 divided by the 14.347. That's what's happening here. So now I need to use some algebra to back myself out of that. I'm going to multiply by the 14 to get that out of the denominator. Oops, 347. You get it. So I need 14.347 times the negative 0.37 That gives me negative 5.30839 is equal to x minus 7.31. And then I'm going to add the 7.31 plus 7.31 gives me almost exactly 2. I ran out of room down here, so I'm going to come up here. I get 2 is equal to x. So the lead level is 2 parts per billion at that standard deviation. Okay, so you can work backwards in this. Sometimes you're going to be given questions that are missing the mean, and you're going to have to work backwards to find the missing mean. Sometimes you're going to be given questions that are missing the standard deviation. You have to work backwards to find the standard deviation. That's just good old algebra, using your algebra skills to back yourself out of missing values and get to missing values. This little AP exam tip that we have up here, it says be sure to interpret the magnitude or the number of standard deviations and direction as greater than or less than and the mean and the z-score in the context. So context of the question. All right, so let's look at another example. Growing like a beanstalk. It says Jordan was 55 inches tall at age 9. The distribution for the height of 9-year-old girls has a mean of 52.5 inches and a standard deviation of 2.5. Zane was 58 inches tall at 11. Distribution of height for 11-year-old boys has a mean of 56.5, standard deviation of 3. Who is taller relative to the other children of their gender and age? Justify your answer. So if you are given 2 different distributions that have different means and different standard deviations and you want to compare them, the way that you compare them is to standardize their score. You need to standardize their scores so that you can look at them at a common point. So if I standardize both their scores, so I'm going to start with Jordan. So Jordan over here, her z-score is going to look like her height, which is 55, minus the mean of 52.5, divided by the standard deviation of 2.5. And if I do that math quick, 55 minus 52.5 divided by 2.5 is 1. So that's exactly a z-score of 1. And if I come over and look at Zane, and Zane's z-score looks like 58 minus 56.5 divided by 3. That's going to be 1.5 divided by 3. I can see it in my head already, but I'm going to do it in my calculator just because, you know, sometimes it's good to check. So 58 minus 56.5 is 1.5. 1.5 divided by 3 is 0.5 for my z-score. Oops. Not 0.2, 0.5. Hello. So 0.5 for my z-score there. So the question is, who's taller? In this instance, Jordan is taller relative to her population. Other children. Children. Her age and gender. Okay, and that's just simply because she's further away from the mean and in the positive direction. She's at a positive 1, he's at a positive 0.5. She's higher above him in terms of standardized score. All right, the last thing we're going to look at for today is cumulative relative frequency graphs. So here's what a cumulative relative frequency graph is. We've talked about relative frequency before. When we take a distribution and we mark its frequency in terms of percents rather than, or proportions, rather than just the frequency or the count. But a cumulative, I want you to think of the word cumulative right here. Cumulative means sum. That's a nice way of saying you're going to add things together or put everything together. So the cumulative relative frequency graph, it's always going to start down here at the 0%, and it's always going to end up here at the 100%. So what you're doing is you're adding each interval's percentage to the previous group as you go. And the curve in the middle is what gives you the shape of how the distribution is changing. But you always start at 0 and you always end at 100, okay? You can mark your points along the way. They have some examples over here. I probably shouldn't have written across my values. Let me erase that so you can see them again. They have some examples over here. The 0.40 signifies the 0 percentile. We marked that one. The 0.45, 4.35 signifies that 4.35% of the president, this was president's data, age when took office. We're going to look at President Obama in the next example. So this is that same graph. And then the 0.8100 signifies that 100% of the presidents who took office at the age of 80 years or younger. So this is the top level there, okay? So let's go to that example with President Obama. It says, Part A was Barack Obama, who first took the office at age 47 years, 169 days, so about 47.463, unusually young. Explain your answer, okay? So here is his marking, okay? You can see they put it on the graph for us. So if you think about this in terms of this being the cumulative relative frequency, unusually young would be underneath the 50th percentile. He's down here at the 11th percentile. So President Obama marks the 11th percentile, and I would say, yeah, that's pretty young in terms of presidents taking office. So what that means is only 11% of presidents took office at his age or younger. At Obama's age or younger, which is fairly young. It's not anything to be an outlier of any kind. I wouldn't call that an outlier, but I would still say that that's on the low end of the scale. That's fairly young. That's pretty young age to take office. And then the next part says, estimate the 65th percentile of the distribution. So to get the 65th percentile, you want to find the 65 over here on your y-axis. There's my 70. I'm going to say 65 is about there. And if I kind of follow it across, I didn't do a super great job with my line, then you're looking kind of at that point right there. And what is that point? Looks like it's about 58-ish. I would call it 58. So the 65th percentile is about 58 or 59 years old. Now, I could probably have done this better if I got out a ruler, or if I were in Notability, I could make that snap that straight line across and then snap another straight line down. It's kind of nice when you do that in Notability. I'm not in Notability to make this video, so it's a little bit harder to see, but you get the point of what you're finding there. So this is to the end of our notes for today. I thank you for listening, and I will catch you next time.